Have you ever wondered why some car headlights, those bright blue ones, cost so much to replace? The answer lies in a rare and remarkable element, xenon. Xenon is one of the noble gases, an element that's full of surprises. In this video we will explore xenon's story from its discovery, the origin of its name, to the unique properties and the many ways we use it today. We'll find out what happens when xenon meets a Teslacoil, and we will see this mysterious gas make certain car lights shine so bright, and why it makes them so darn expensive. Welcome to Cube Chemistry, where we will discuss all the elements of the periodic system and also do experiments. So if you like this video and want to see more, make sure to like, subscribe and hit the notification bell so you will never have to miss another episode. Also make sure to fill in the poll in the post section of the channel for next week, as we will be discussing another element again. This will be the last poll of the year, as we will go on a well-deserved holiday to the US. But not to worry, the episodes will be here on the day before Christmas and New Year's Eve. So what we have here is a cube like always, but it has been quite some time since we had a cube like this, or discussed one like this. At the first sight, the cube seems to have an empty tube in it. If the guys from Engineered Labs did their job right, it actually has a gas in it, and that gas is the noble gas, xenon. Yeah, Jeroen, that is all very interesting, but what we are here to find out is, can you lick it? Well, even though xenon is completely non-reactive, you might wonder whether you can actually taste or even lick it. Well, the truth is that you really can't. Xenon is a gas at room temperature, so it won't stay on your tongue long enough for anything to happen. It has no flavor, no smell, and no chemical bite, because it's a noble gas. But more importantly, you should never stick your face into a container of xenon to try it. Xenon may be harmless chemically, but it's also a powerful anesthetic that can push oxygen out of your lungs. Inhaling too much of it can make you lightheaded, disoriented, or even unconscious in seconds. And if we're talking about liquid xenon, that is even more dangerous. At more than 100 degrees below the freezing point, it would cause instant frostbite. So while it's a fun question, and the periodic leaking table seems to be positive about this, licking xenon is really just one of those things better left to the imagination. The tale of xenon begins at the end of the 19th century. Back in 1898, two chemists in England, Sir William Ramsay and Maurice Travers, were on a quest to find new gases hidden in air. They used a powerful machine to chill air until it became a liquid. Then let it slowly evaporate, and as the liquid air boiled off into stages, they caught gases that came out at different points. They've already discovered neon and krypton this way weeks earlier, and finally, in July 1898, they detected a tiny bit of an unknown gas in the last remaining residue of their experiment. This was a new element, xenon. Ramsay and Travers immediately realized this gas was extremely rare. Ramsay estimated at the time that xenon made up only 1 part of 20 million of the Earth's atmosphere. Modern measurements show it's a tiny bit more common, roughly 1 in 11 million, but still incredibly rare. Now, to put that into perspective, imagine a huge balloon filled with 20 million parts of air. Only 1 part would be xenon. No wonder it took such large amount of liquefied air to isolate just a minuscule sample of xenon. They nearly missed it entirely, as xenon only revealed itself in that final fraction after most of the liquid air had boiled away. Now, upon discovering this strange gas, Ramsay chose the name xenon based on the Greek word xenos, which means stranger or foreigner. The name was perfectly fitting. Xenon was truly a foreigner, hiding in plain air yet undetected until their experiment. With xenon's discovery, Ramsay and Travers had added one more member to the family of noble gases, which at that time included helium, neon, argon, and krypton. Radon would be discovered a bit later. It was an exciting addition to the periodic table in 1898. For many years after its discovery, xenon remained more of a scientific curiosity than a practical material. It was rare and hard to obtain, so there wasn't much you could do with it at first, but as we will see, that changed as scientists learned more about this mysterious gas and found clever ways to use its special properties. So what exactly is xenon like? Well, xenon is a chemical element with the symbol Xe and atomic number 54. It belongs to the group of elements known as the noble gases, the same family as helium and neon. And like its noble gas cousins, xenon is a colorless and odorless gas at room temperature. One of the first things to know about xenon is that it's heavy. Well, for a gas anyway. Xenon atoms are large and contain many protons and neutrons, which makes xenon gas much denser than air. In fact, xenon is about 4.5 to 5 times heavier than the air that we breathe. If you could fill a balloon with xenon and it didn't leak, the balloon would actually feel noticeably heavier and would not float at all. Because it is so heavy, xenon behaves a little bit different than lighter gases. For example, sound travels through xenon much slower than through air. That means that if someone inhales a bit of xenon, not a good idea to do casually by the way, their voice would become deep and low, the opposite effect of inhaling helium, which makes your voice high-pitched. This voice-changing trick with xenon is due to physics. The speed of sound in xenon is only half of that in air, lowering the pitch of the voice. Xenon has ever been used as an anesthesia gas in medicine, so you definitely don't want to breathe it in for fun. It can literally put you to sleep. Xenon can also be turned into a liquid and even into a solid if it's cold enough. It has a boiling point of about minus 108 degrees Celsius, minus 162 degrees Fahrenheit. So if you chill xenon gas below that, it condenses into a clear, colorless liquid. Go even colder, below minus 111.8 degrees Celsius or minus 169 degrees Fahrenheit, and that liquid xenon will freeze into a solid, which looks like a waxy crystal. These are laboratory curiosities mostly, but liquid xenon does have uses, for instance, in certain particle physics detectors. Large tanks of liquid xenon are used to detect rare interactions. Now, chemically speaking, xenon is often described as inert. A xenon atom has a full set of electrons in its outer shell, 8 electrons, satisfying the so-called octet rule, which makes it very stable and not eager to go form compounds. Under normal conditions, xenon won't burn or react with other elements. You could bubble xenon through acid or set an open flame in it and nothing would happen. Xenon just doesn't want to bond with other atoms under ordinary circumstances. For a long time, chemists believed xenon and the other noble gases could not form any compounds at all. They were thought to be completely unreactive. However, xenon isn't totally aloof. It just needs extreme conditions or very reactive partners to coax it into a chemical relationship. In 1962, a chemist named Neil Bartlett shocked the scientific world by making xenon react with fluorine, one of the most reactive elements. He created the first xenon compound, a yellow solid known as xenon hexafluoroplatinate. This discovery proved that xenon could indeed form chemical bonds, overturning the old belief that noble gases were entirely inert. Following Bartlett's breakthrough, many xenon compounds were synthesized. Xenon can form fluorides like these and oxides like these, among others. These compounds typically require special conditions to form, very high pressures or powerful reagents like fluorine gas. They are often quite unstable. Xenon really prefers to be free as a noble gas, and some will decompose explosively if you're not careful. Nonetheless, they exist, and they show that xenon isn't as completely untouchable as one thought. Still, in everyday life, you won't encounter xenon compounds. Xenon gas mostly minds its own business, unless it's in a chemist's lab or inside special equipment. One small chemical role for xenon in daily life is inside incandescent light bulbs. Some high-quality incandescent light bulbs and projector bulbs are filled with xenon gas instead of cheaper nitrogen or argon to prolong the filament's life and increase efficiency. The xenon gas inside the light bulb helps to prevent a hot tungsten filament from evaporating too quickly, which means the bulb can burn brighter and last longer. It's a minor use compared to others, but it's a neat example of xenon's inertness being useful. The gas won't react with the filament, and its heaviness helps keep the tungsten from dispersing. One of xenon's most striking traits appears when you run electricity through it. If you've ever seen xenon gas inside a glass tube with a high voltage applied, for instance in certain lamps or science demonstrations, you'll notice a brilliant blue glow. When xenon atoms get excited by an electric charge, they emit light. Different gases glow in different colors. For example, neon light lights up bright orange-red, and xenon's glow is a beautiful blue or lavender-purple color. We can demonstrate this with a Teslacoil. A Teslacoil is a device that creates a high-voltage electric field image holding a small tube filled with xenon gas near a buzzing Teslacoil. Don't try this at home without proper safety precautions. Now, of course, we got a Teslacoil, and as the Teslacoil releases the energy, the xenon in the tube suddenly comes alive with luminous color. It shines with a ghostly blue-violet light. What's happening here? Well, the electric field from the Teslacoil is energizing the xenon atoms, knocking electrons to higher energy levels. When those electrons fall back down, the xenon atoms release energy as photons of light. Xenon's light spans many colors, but the strongest is in the blue part of the spectrum. So our eyes see a vivid, cool toned glow. It's a captivating sight, a noble gas giving off a neon-like light show. This glowing property isn't just for the show, it's fundamental to many xenon applications. Xenon's ability to emit bright light when zapped with electricity is exactly why we use it in certain lamps and flashbulbs. Now, if xenon is so important for high-tech lights and other uses, where do we get it from? Short answer is the air. But it's a bit like finding a needle in a haystack. Xenon is present in the Earth's atmosphere, but only in trace amounts. Now, as mentioned earlier, it's about this percentage of air, and that is 86 parts per billion. Visualize that if you had a billion liters of air, only about 87 liters of it would be xenon. Put it in another way, in every 11 million or so atoms in the air, only one of them is xenon. It's incredibly scarce in our environment. Interestingly, for reasons scientists are still investigating, Earth actually has less xenon in the atmosphere than expected. Other bodies in the solar system and ancient meteorites suggest there was more xenon present when the Earth was formed. So where did a lot of the xenon go? Now, this is a little scientific mystery, often called the missing xenon problem. Some theories suggest xenon might be hiding in plain sight, trapped in minerals underground. For example, xenon bound up with quartz or iron deep in the Earth's crust or mantle. Another idea is that a lot of xenon escaped into space early in Earth's history. There's also evidence xenon can get caught in ice or clathrate compounds. It's an ongoing puzzle, and researchers are still trying to solve it. But whatever the case, the xenon we can easily access is mostly the tiny amount floating in air around us. Now, because xenon is so rare in air, obtaining it is a challenge. We can't mine xenon out of the ground like gold. Instead, we literally have to pull it from thin air. The primary method to get xenon is through fractional distillation of liquid air as part of an industrial gas process. Companies start by cooling air down until it becomes liquid around minus 196 degrees Celsius, which liquefies nitrogen, and minus 183 degrees Celsius for oxygen. As the liquid air is warmed up in distillation columns, the major compounds boil off one by one: nitrogen, oxygen, argon, etc. Xenon, being one of the heaviest gases with a low vapor pressure, stays in the liquid phase until almost everything else is gone. It ends up concentrated in the final leftover liquid along with krypton, another rare noble gas. By using additional distillation steps or chemical absorption techniques, that krypton-xenon mixture can be separated into pure krypton and pure xenon. The whole process is elaborate and requires a lot of energy, equipment, and huge volumes of air. The result is that only a very small yield of xenon is obtained for a given amount of air processed. Globally, the supply of xenon each year is on the order of 50 to 70 tons, which is tiny considering the thousands of tons of other gases produced. It's also interesting to note that xenon exists out in space. The atmosphere of the planet Jupiter, for instance, has a relatively high concentration of xenon, much more than the Earth's. Xenon in the cosmos is created by rare nuclear processes, like the explosions of supernovas and the slow radioactive decay of elements. But out there, xenon just drifts in gas clouds or gets trapped in planets. We can't harvest it. Our xenon supply is basically tied to how much we can extract from air or produce as a byproduct of other processes. And now we can answer our original question. Why are xenon car headlights, those HID lights so darn expensive? It comes down to everything we've discussed. Xenon is a rare element that requires a lot of effort and energy to obtain. When you buy a xenon headlight bulb, you're paying for a little bit of one of the rarest ingredients on Earth. You're also paying for the advanced technology needed to use that xenon gas to produce light. A xenon headlight bulb is not a simple glowing filament like an old-fashioned bulb. It's a high-intensity discharge HID lamp, which means it creates an extremely bright electric arc between two electrodes inside a bulb filled with xenon gas, along with a few other gases or salts. When that arc jumps through the xenon gas, the gas lights up brightly, similar to our Teslacoil demonstration, but in a controlled, continuous way. The result is a bright white blue light that can be up to 3 times brighter than a traditional halogen headlight. Now, because xenon gas is so scarce, the bulbs themselves cost much more to manufacture. But that is not the only factor. Xenon headlights also require specialized electronics called ballasts to ignite and power that arc. A car with xenon lights must have a high voltage igniter to start an arc on the order of 20,000 volts for a brief moment, and then the ballast to keep the arc running steadily. Now, this system adds cost and complexity to the vehicle. Additionally, regulations in many countries require that very bright xenon headlights have auto-leveling systems to automatically adjust the aim of the lights and avoid blinding oncoming drivers due to their intensity, and also have headlights washers. The washers are required because even a small amount of dirt on a headlight lens could scatter the intense light and cause glare for other drivers. By keeping the lights clean, the beams stay focused. These extra features, leveling motors, sensors, washer systems, all add up to the expense of a xenon lighting setup. In short, when you opt for xenon headlights, you're buying into a premium technology. The upside is that you get a very much brighter, whiter light that can make night driving easier and safer. Xenon lights have a longer reach and a wider spread than typical halogen lamps, helping drivers to see road signs, lane markings, and potential hazards sooner. They also tend to last longer than halogen bulbs because there is no fragile filament to burn out. But the downside is the cost. If one of the bulbs fails or the ballast needs replacement, it can be quite pricey compared to the old $10 halogen bulb you might have been used to. It's worth mentioning that newer technologies like LED headlights are becoming common, and those can also be expensive, especially when they first appeared on luxury models. However, LED costs have been dropping, and they have certain advantages like energy efficiency and a very long life. In many modern cars, LED lights are replacing xenon lights as the top-end option. That said, xenon HID lights still remain in use and are still known for their incredible brightness. Now that you know the background of the high costs of xenon headlights, and they make sense, it's not just a marketing gimmick. It reflects the real rarity and complexity behind that brilliant glow. Car headlights might be one of the more visible uses of xenon, literally and figuratively, but this element finds use in many other fascinating places. Here are some of its major applications and uses for xenon. Ever been momentarily blinded by a camera flash? There's a good chance that flash was powered by xenon. Xenon flash lamps are used in photography to produce a quick, intense burst of white light, perfect for illuminating a scene in a fraction of a second. The famous engineer Harold Edgerton invented the xenon flash lamp in the 1930s, enabling high-speed photography. Think of those iconic images of a bullet piercing an apple or a droplet of milk forming a crown. They use xenon flash to capture those split-second moments. Xenon flash tubes are still used today in camera flashes and strobe lights for events, concert, and emergency vehicle lights. They can deliver extremely bright pulses of light by discharging a high voltage pulse through xenon gas, making night turn into day for an instant. Now, if you've ever sat in a big movie theater, especially an IMAX theater, or seen a powerful searchlight beam sweeping across the sky, xenon is likely at work. Xenon short arc lamps became the standard light source for cinema projectors starting in the 1950s and the 1960s. These lamps create a continuous intense light by sustaining an electric arc in high-pressure xenon gas. The light from xenon arc lamps is very bright and very white, with a spectrum that resembles natural daylight. This is perfect for projecting films with an accurate color and clarity. Before xenon lamps, theater used carbon arc lamps, which were labor-intensive and less stable. Xenon made projectors brighter, simpler to operate, and more reliable. Similarly, xenon arc lamps are used in giant searchlights and spotlights, basically anywhere you need an extremely high-intensity beam of light, like indoor events or to simulate sunlight in product testing. Those flat plasma screen TVs that were popular before LCD and LED screens took over, they also use xenon. Each tiny pixel cell in a plasma display contained a mixture of xenon and neon gas when the TV was on. An electrical charge would excite the gas in the cells, causing the xenon neon gas to release ultraviolet light. That UV light then hit phosphor coatings on the cell walls, which glowed to produce visible light of various colors, forming the picture on the screen. So xenon was quietly helping people watch their favorite TV shows and movies in those early big screen plasma TVs. Xenon plays a role in the world of lasers in a couple of ways. First, as mentioned, xenon flash lamps were used to pump some of the first lasers. First laser, built in 1960, a ruby crystal laser, used a xenon flash tube to energize the ruby medium and create a laser beam. Later on, xenon flash lamps became more common for pumping other solid-state lasers, and even today, some laser systems use xenon lamps for this purpose. Second, xenon itself can be part of certain lasers, specifically excimer lasers. In excimer lasers, a noble gas like xenon or krypton is combined with a halogen like fluorine or chlorine to form an excited dimer molecule, for example, xenon chloride. These excited molecules can laze, emitting a powerful pulse of ultraviolet light. Xenon excimers lasers, such as xenon chloride lasers, have been used in applications like laser eye surgery, dermatology, for treating skin conditions, and in microelectronic manufacturing for etching fine patterns with UV light. Also, researchers discovered in 1962 that pure oxygen gas could produce laser action in UV range when excited under the right conditions. So, this inactive gas proved quite active in laser science. One of the coolest uses of xenon is literally out of this world. It's used to fuel ion thrusters on spacecraft. Ion thrusters are a type of engine that provides gentle but efficient thrust by ejecting ions, charged atoms, at high speed. Xenon is the propellant of choice for most ion engines, for example, those used on NASA's Deep Space One probe, the Dawn mission to the asteroids, and many satellites that need to adjust their orbits. Why xenon? Because it's inert, so it won't corrode or degrade the engine's components. It's heavy. Each xenon ion provides more kick due to its mass compared to lighter gases, and it can be ionized with relatively low energy. Xenon has a low ionization energy than many other gases, meaning you can strip an electron of a xenon atom fairly easily to make it an ion. In an ion thruster, xenon gas is fed into a chamber where electrons from a cathode knock electrons off the xenon atoms, turning them into positive ions. Then an electric field accelerates those xenon ions out of the back of the engine at extremely high speed, up to 30 to 40 kilometers per second, creating thrust. The thrust from an ion engine is gentle, comparable to the weight of a sheet of paper or a small coin in your hand, but it can be applied continuously for months or years. Over time, that continuous push lets the spacecraft reach very high speeds, using only a modest amount of propellant. Xenon enables missions that wouldn't be possible with conventional chemical rockets. The only downsides are that xenon must be carried along, adding weight, and it's costly. For instance, the Dawn spacecraft carried about 425 kilograms of xenon fuel on board, but the efficiency of ion propulsion is so high that it's worth it for certain tasks in space. Now, xenon might be too expensive to put in everyday light bulb, but in medicine, its unique properties find special uses. One interesting application is in anesthesia. Xenon gas is actually a remarkable anesthetic agent. Inhaling a mixture of xenon and oxygen can quickly and safely put a patient into unconsciousness for surgery. Xenon has some big advantages as an anesthetic. It works fast, it doesn't trigger harmful reactions in the body, and when the surgery is over, it can be flushed out and even recovered. Since it's so pricey, modern xenon anesthetic machines actually recapture and recycle the gas. It also has no environmental impact, unlike nitrous oxide, laughing gas, which is a greenhouse gas. Xenon released into the environment just returns to the atmosphere it came from, causing no harm. Additionally, research has found xenon has protective effects on the brain. It can reduce neuronal damage in situations like stroke or trauma, which means it might help protect patients' brains during certain surgeries or after injuries. The catch with xenon anesthesia is, of course, cost. Xenon is vastly more expensive than usual anesthetic gases, so while a few hospitals, notably in Europe and Japan, have used xenon in their anesthesia systems, it's not widespread. Beyond anesthesia, xenon is used in medical imaging. In the past, doctors employed a radioactive isotope, Xenon-133, in lung ventilation scans. A patient would inhale a tiny amount of Xenon-133, and because it emits gamma rays, a camera could track how the gas moved through the lungs, helping to diagnose lung function issues. More cutting edge is the use of hyperpolarized Xenon-129 in MRI scans. Xenon-129 is a stable non-radioactive isotope that can be hyperpolarized, meaning its atoms are aligned to massively increase the MRI signal. A patient inhales this hyperpolarized xenon gas, and then MRI images can actually visualize the air spaces in the lungs and even how xenon dissolves into the blood and tissues. This technique can produce detailed images of lung structure and function, offering insights for conditions like asthma, fibrosis, or COPD. It's still a research and specialized tool due to the complexity and, yes, the cost of xenon, but it shows how versatile this element can be. Xenon helps out in scientific experiments and even in monitoring for nuclear explosions. For instance, physicists building detectors for elusive dark matter particles use xenon in an interesting way. Experiments like the Xenon 1T in Italy or LUX in the US have huge tanks filled with ultra-pure liquid xenon. The idea is that if a dark matter particle, which hardly ever interacts with normal matter, passes through and hits a xenon atom, the collision will make a tiny flash of light and free some electrical charge, which the sensitive detectors can pick up. Xenon is great for this because it's heavy, more likely to interact with a hypothetical heavy dark matter particle, and it scintillates, produces light very cleanly when struck. So far, dark matter hasn't been definitively found, but those xenon-based detectors are among the most sensitive ones in the world for that search. Another use of xenon is in detecting nuclear activity. When a nuclear bomb is tested or a nuclear reactor runs, certain isotopes of xenon are produced as fusion byproducts. Xenon gas can seep out from the underground nuclear test or be released from a reactor, and because it's a noble gas, it drifts through the air without reaction. International monitoring stations collect air samples and look for signatures of radioactive xenon isotopes as a clue that a nuclear test might have occurred. This helps to verify treaties and keep watch on nuclear proliferation. It's fascinating that an element as noble and literally noble gas as xenon can serve as a spy, tipping us off to secret nuclear events from afar. Now here's a rather unexpected way xenon popped up in the news: sports doping. Around 2014, reports emerged that some athletes, notably in Russia, were inhaling xenon gas to try boost their performance. It turns out that breathing a mixture of xenon and oxygen for a few minutes can trick the body into thinking that it's at high altitude, because xenon causes a slightly short-term deprivation of oxygen, hypoxia. This in turn triggers the body to produce more erythropoietin, a hormone that increases red blood cell production. Now, more red blood cells means more oxygen can be carried in the blood, potentially improving endurance, the same goal athletes have when they train at altitude or take synthetic EPO as a drug. The World Anti-Doping Agency got wind of this, and even though it sounds bizarre, they officially banned xenon and argon inhalation for performance enhancing in 2014. It's hard to know how common this practice was or how effective xenon really is as a doping agent. There's not a lot of scientific evidence that it significantly boosts human performance, and inhaling xenon unsupervised could be quite dangerous. Remember, it's an anesthetic, too much, and an athlete could pass out. Nonetheless, it's a testament to the unusual places xenon has shown up, from outer space engines all the way up to Olympic training rooms. In nuclear reactors, xenon can become a serious problem because one of its isotopes, Xenon-135, is an extremely powerful neutron absorber. As uranium atoms split during normal reactor operations, Xenon-135 builds up and begins soaking up neutrons that are needed to sustain the chain reaction. Now, this effect called xenon poisoning or reactor poisoning can cause reactor power to drop sharply and can even make a reactor impossible to start for several hours until the xenon naturally decays. Now, this phenomenon played a major role in the Chernobyl disaster. The reactor had been held at low power for too long, allowing Xenon-135 to accumulate to dangerous levels. Operators tried to counteract this by withdrawing far too many control rods, pushing the reactor into an unstable state. When the Xenon-135 suddenly burned away during the test, its braking effect vanished, causing a rapid surge in power that the compromised reactor design could no longer control. Moments later, the reactor exploded. Thus, xenon poisoning didn't cause the accident on its own, but it was a critical factor in the sequence that made the catastrophe possible. Now, a great explanation about this accident is in the 5th and final episode of Chernobyl from HBO. By all means, watch it. It's a great series. In the world of elements, xenon truly lives up to its name, a once mysterious stranger that turned out to be brilliantly useful. From deep under the ground to high up in space, xenon has made its mark. It reminds us that even the most elusive materials can find a purpose, and that sometimes a little flash of light from an odd corner of the periodic table can have an outsized impact on technology and our daily lives. Now, we would like to thank the members that support our channel. Thanks for doing that. We really appreciate you. Now, if you think we missed anything, tell us in the comments, and if you want to know about another noble gas, take a look at this old video of neon next.